Hello world, my name is Niam. For the past year and a bit, I've been preoccupied with my generator system. A kinetic electromechanical generator that is able to generate usable power anywhere and at any time. On the topic of energy harvesting, here's a quote from my favorite YouTubers, Great Scott.
At the beginning, we obviously need a harvester, which turns our source energy into raw electrical energy. Then we need a conversion circuit that takes our raw electrical energy, which was maybe an AC voltage, and turns it into a DC voltage, which we can then use to charge up the next part of the system, the energy storage. This can be a normal or supercapacitor with enough capacity to power the last part of the system, the electronic load.
To fulfill this grand objective, we need what is called an integrated circuit, which is essentially a whole bunch of electronic components, diodes, capacitors, resistors, inductors, packed into a very small footprint. In this case, I'm using the LTS3588 chip, an all-in-one microchip that has voltage regulation, DC to DC conversion, and rectifying all included in one single footprint. If you can't tell, this chip was specially made for energy harvesting. And if you've been watching this series lately, you'll know that my generator consists of two main generators, the triboelectric generator and the piezoelectric generator. Let's start with the triboelectric generator. This triboelectric power source leads to this full bridge rectifier, or as some like to call it,
a full bridge rectifier. A full bridge rectifier.
It's a simple series of diodes which rectifies AC voltage or alternating voltage into pulsating DC voltage or direct current voltage. Diodes act as a one-way valves, allowing current to flow in one direction but not the other. This arrangement of diodes allow current to flow in the same direction on both halves of the AC sine wave. During the positive half cycle, two diodes conduct, while the other two conduct during the negative half cycle. This capacitor replaces the load on the ends of the bridge rectifier. By acting as a reservoir smoothing out voltage, the bridge rectifier outputs pulsating DC voltage. The capacitor charges to its peak voltage during diode conduction, then discharges during the voltage dips. This creates a near constant voltage level. The capacitors connected to V1 and V2 pins of the IC act as even more reservoirs. The triboelectric generator produces energy only when it experiences mechanical force. Therefore, electrical current is constant. Both capacitors collect charge until they reach their voltage level, where they then discharge. This then triggers the buck converter inside the IC, so this buck converter is built in. As mentioned before, the LTC35881, my chip, is an IC specially designed for low power generators. It has a built-in rectifying circuit, low voltage undercurrent detecting circuit, and a DC-DC regulator circuit. This being said, this IC was designed for piezoelectric and solar applications, which don't have as high a voltage output as triboelectric generators. This is why external rectifying circuits were used. However, the high-efficiency buck converter is used within this IC, regulating voltage while increasing current. The chip stays below a certain voltage threshold before the capacitors have been charged. This reduces power consumption of the chip. The components connected to the SW and output pins store output energy from the IC. Because the buck converter inside the IC switches DC voltage constantly to regulate voltage, the inductor stores output energy magnetically during the switching cycle to ensure a smooth output to the output capacitor. The large capacitor or output capacitor stores energy acting as a buffer, smoothing output voltage for the output. Now, you may be seeing this final
A full bridge rectifier.
Haven't we already converted AC voltage into DC voltage? We have. However,
A full bridge rectifier.
can be used for a plethora of different things. This final rectifying circuit protects polarity switching. If the output terminals become switched in the process of powering a device, this rectifying circuit also prevents backloading, where current flows back when the circuit is under a load and no power is being generated. This entire circuit transforms inconsistent hundreds of volts into a manageable, steady output power that is seen at output terminals. This is a piezoelectric energy harvester. Here we have piezoelectric outputs and AC input source of power. Now these are the leading ends of the electrodes attached to the PVDF film. These terminals lead into the PZ1 and PZ2 pins from the LTS 3855. While this portion of the circuit may look a bit mystic, remember that this integrated circuit is a layout of different components that are equivalent to a larger circuits. These PZ1 and PZ2 pins connect to the input pins of a bridge rectifier is within this chip. Now within this chip, the PZ1 and PZ2 pins are connected to the VIN pins over here, which receives pulsating DC current from the bridge rectifier. Connected to the VIN and HEN pins, we have the 22 microfarad capacitor that, similar to the triboelectric circuit, smooths the inconsistent pulsating DC voltage produced by the full bridge rectifier. The VIN then releases another current, which is then supplied to this chip's buck converter. Connected to the cap and AGND pins, we have a capacitor number 2, rated as 4.7 microfarad. The capacitor isn't used as a reservoir. Instead, it's used to stabilize power for the switching controller to generate signals to power such a buck converter. This switching controller is connected to the larger DC-DC converter, which regulates voltage output. You see, piezoelectric sources generate unstable high voltages and low current. Now, these high voltages aren't as high as triboelectric high voltages, but they're still quite high. This is because when charge per mechanical strain is tiny, the voltage potential produced by the PVF is much longer. This is why a buck step-down converter is used to regulate output voltage and to amplify output current. It does this by burning excess voltage via mechanical MOSFETs within the buck converter. Put it simply, excess voltage is put into mechanical motion. Because this is a mechanical switch we're talking about here, when the mechanical switch turns on and the current flows through, the attached inductor's magnetic field collapses, pushing power into the output terminals. It's the inductor's job to store power like a capacitor, though through a magnetic field, unlike a capacitor. The final capacitor, 47 microfarads, smooths the switching power from the buck converter, providing a relatively smooth energy output. This final capacitor, 47 microfarads, smooths the output power from the buck converter, providing a relatively smooth energy output. The energy circuit ends with the output terminals, with the positive output terminal being the one right to the inductor, while the negative or ground terminal being the one near the right of the inductor. That's great! Now we have 2 circuits to finally start managing electricity, right?
False.
Unfortunately, because the triboelectric generator is so much different from the piezoelectric generator and the way it outputs energy, you can't just connect the 4 output terminals together and expect results. I'm actively trying to design a new unified circuit that takes those 4 outputs and converts it into 2 unified power outlets. Because if you remember, my objective isn't to create 2 separate devices, it's to create a hybrid piezoelectric and triboelectric generator. The solution to my situation is said by none other than fictional character Mark Watney.
In the face of overwhelming odds, I'm left with only one option. I'm gonna have to science the shit out of this.
And that's what I'll do. Until I figure this out, stay curious, and I'll see you in the next one.